Hello, everyone. Hello, everyone. Today we have a very special session prepared for you. We currently are at the CEDEX Geotechnical Laboratory, where we are going to share with you all the details of the Peddler project. As our presenters, we have José Estaire, the current director of CEDEX, and Raúl Murciego, sales director of infrastructure projects in Spain. Please feel free to send your questions during or after the video, and we will do our best to answer as many as we can. Also, we have available captions in different languages, so activate them if you need them. However, this option is in testing mode, so it might not be 100% accurate.
Good morning, everyone, and welcome. We are in Madrid, in CEDEX Trackbox. This is a great facility of geotechnical laboratory of CEDEX. Well, this is a unique environment where we move from theory to a real scale validation. Here we have been testing a lightweight embankment under demanding conditions to better understand its behavior in railway application. To help us to go deeper into this, we are joined with a key expert. Today we have José Estaire, recently appointed Director of Geotechnical Laboratory. José, first of all, congratulations for your new role. And thank you very much for giving us the opportunity to be here and sharing these facilities and your experience and your expertise.
Thank you very much for your words, and welcome to this testing facility, which is named, as Raúl has said, CEDEX Trackbox, and later on I'll explain the main characteristics of it.
Okay, José, to start with and help everyone to understand where we are, could you explain what the Trackbox is, how it works, and why it's such a unique facility for testing a railway solution? But maybe we can go inside the facility.
Okay, so come with me to the inside part of the testing facility, and then I'll explain there. So we are now in CEDEX Trackbox. CEDEX because we are in CEDEX, Track because the main objective of this testing facility is to determine the characteristic of the behavior of the railway track sections, as the one we have below us. And Box because everything that we can see here is inside a huge metallic box, which is 21 meters long, 5 meters wide, and there are 4 meters deep. In these 4 meters, we are able to build a real embankment, a real foam layer, and then the subballast and the ballast layer, as you can see here. Then we can install the sleepers and the rail, and the sleepers and the rail are elements only to transmit the load produced by these 6 actuators to the section. Actually, the main part of the installation are these 3 pairs of actuators with which we simulate the pass-by of trains. If we stand up in this central section, we can model with these first 2 actuators the approaching of the train. Then the train, let's say, its model passing by this central section, and then there is a departure of the train model by that pair of actuators. Each of these actuators can impose a load of 25 tons. So the couple is able to produce 50 tons, which is more than the double of the load imposed by a freight train. So with this system, we can model both passengers and freight trains. The other important characteristic is the speed. A usual high-speed train takes around, when it travels at 300 kilometers per hour, takes around less than 3 seconds to pass by along a section. And this type of trains has usually around 30 or 35 axles. So we have to take into account that in those 3 seconds, the system must impose 35 times a load of 16 tons. And if we increase the speed to 400 kilometers per hour, that time decreases to less than 2 seconds. So when we model trains passing by at 400 kilometers per hour, the system should impose loads 35 times in less than 2 seconds. That's why our record of modeling speed is 400 kilometers per hour. So as a summary, we can model both freight and passenger trains from speeds from 0 to 400 kilometers per hour.
And Jose, one question. We can find another similar facility in Europe, like this one?
No, this is the only testing facility like this one in Europe. There is another one similar in China, but this is the only one in Europe that and that's why we work for all the administrations of railways in Europe.
And which year this facility start to run and produce this knowledge about trains, railways?
Well, the testing facility was designed and built in the frame of a European project in 2004, so around 20 years of functioning now. And and in these 20 years we have worked a lot of time, we have made a lot of tests for different railway European administrations and also for private companies as LECA for, let's say, particular projects.
Okay, and you explain about the actuators, you explain about how to apply the loads, but how do you find this
results, you mean?
Yeah.
During the test, we install instrumentation both in the surface of the section and also inside the layers.
Inside the embankment?
Inside the embankment.
Okay.
We measure displacement, velocities and accelerations with different kinds of LVDTs, potentiometer and laser system. For the speed of the movement of the different elements, we install geophones usually in the rail and in the sleepers. And also, when we want to measure accelerations, we install accelerometers. And the other type of equipment that we usually install are pressure cells to measure the pressure that is imposed by these actuators when we model the pass-by of trains. During the test, the actuator is placed on this metallic element which resembles the shape of the wheel of the train. So the contact between the rail and the wheel is exactly the same as in the reality.
Jose, let's go, and you can explain there the different elements to produce the measurement, the instrumentation.
Here on the table there are some examples of the instrumentation we used during the test. Here, these two pieces are the laser system to measure the displacement of the rail. This is a potentiometer. We use them to measure the movement of the under rail part. Here some LVDTs to measure displacement of the layers. Here there is a geophone to measure the speed, the speed of the movement, both in the sleepers and in the rail. Here there is a accelerometer. And also, this is a very, let's say, specific equipment. This is a real ballast particle, which is equipped with an accelerometer to measure the accelerations of this particular specific ballast particle that we usually install inside the ballast layer. And finally, you can see here one of the pressure cells we install usually in the interfaces of the different layers that compose the railway section.
We can talk about the materials that the section we use a standard ballast. It's a standard ballast like this one, and of course the main objective was check Leica material. Can you share with us your experience, the experience of FedEx about Leica? Because this is a material, the standard material that we use in Spain to reduce loads in different infrastructure projects. The density is 275 kilograms per cubic meter, 37 degrees in the internal friction angle. Can you share with us your experience, the experience of the Laboratory 30 about this material?
Well, taking advantage the test that we perform here in FedEx TrackBox, in the last years we have also made some tests on the specific aggregates, on the specific grains, sorry. And we have broken more than 1,000 grains with different loads, and we have we have modeled this behavior of the grains before trying to understand the global behavior of the aggregate. And in those more than 1,000 breaking tests, we have seen that these materials, these particular grains, are very stiff, and the resistance is also very, very high.
Because this material can be tested in big cells, like a standard aggregate, right?
Yeah, I mean,
it's a different test.
Yes. In addition to this, to the test performed with the grains, we have also performed some tests with triaxial cells and also with big direct shear boxes, because the size of the grains is a bit greater to use, let's say, normal devices. So we have performed triaxial tests and also direct shear tests with big boxes and big equipment to avoid any problem of scale.
Okay, great. Let's go to talk about Peddler. Peddler is standards for performance-based design of lightweight embankment for railway infrastructures. Well, in this framework, we are using Leica as a lightweight aggregate with distinctive properties such as a low density, high strength to weight ratio, and high friction angle. Okay, these characteristics make it particularly interesting for infrastructure application, helping to reduce loads, improve stability, and make infrastructure more resilient. Well, with this in mind, could you explain the main objective of Peddler project And could you describe the section that we test in the facility? Okay.
Yeah. Well, the main objective of this project, PETLER, was to analyze the behavior of this LECA material when it's inside a railway section that is going to suffer the loads from high-speed trains. The main important issue here is that LECA has been used for many years in railway sections for, let's say, normal speeds, but here the focus is the performance of this material when we model high-speed trains. The section that we have here, we constructed here in our facility, is composed in the upper part as is a normal, let's say, a usual high-speed section with a foam layer, subballast layer, 30 centimeters each of them. Then say normal ballast layer, and on top of that, the sleepers on rails. The main difference is that usually below the foam layer there is an embankment, earth embankment usually, and here we have substituted the earth embankment by a layer composed by this lightweight LECA material of 1.1 meter. And that's the focus of our test is to analyze the behavior of this layer.
Because this section is the same that ADIF is using in their high-speed lines,
yes.
right?
Yeah, that's why I have said that the top part of the section is exactly equal to the ones that our Spanish Railway Administration uses in the Spanish high-speed lines.
Because TEDx have a lot of experience in this type of tests with a standard embankment.
Yes.
And now finally the challenge is the behavior of this lightweight aggregate.
Yeah.
Okay.
And taking advantage of our experience in, let's say, normal or usual high-speed sections, we can compare the results that we are going to obtain with this LECA material with the usual sections.
Because in this section, what type of test
we have performed?
Yeah.
We have performed 3 types of tests, as you can see here in this page. A static test to analyze the dynamic characteristics of the section, and also fatigue test.
Jose, regarding the static test, what would you highlight as the most relevant results?
Okay, we have performed a static test during all the testing program. At the beginning, in the middle, in different moments. What we obtain from the static test is the track stiffness as a magnitude that shows us the quality of the behavior of the section. In general, the values obtained are around between 90 and 100 kilonewtons per millimeter, which is the usual value obtained in the, let's say, Spanish high-speed lines. And in the last test, after the fatigue test, that track stiffness decreased a bit, and we obtain a value of 80 kilonewtons per millimeter, which is a acceptable value, but in the, let's say, in the low range of acceptance.
Okay, but previous of this static test, we have to do a stabilization of the line, right?
Yes, of course.
How TEDx did this stabilization?
Well, we use two ways. We use this stamping machine.
This big machine.
This stamping machine that is there, and also after the damping of the ballast layer, we stabilize the the section by passing by trains, 100,000 tons of trains, and actually we obtain an increase of the track stiffness around 20 or 25 kilonewtons per millimeter, up to that value, which is the acceptance value.
Okay, Jose. Moving now to the dynamic behavior of the railway section. How do you approach the study of this dynamic characteristic in the track box?
Well, usually, as you can see here in some of these graphs, when we want to analyze the dynamic characteristics of the section, we model the same type of train with different speeds. Here in this case, from static to 400 kilometers per hour in steps of between 25-50 kilometers. We have modeled 14 speeds. And what we try to analyze is the increase of these magnitudes with the increase of the speed. The theory says that there must be an increase, and what we usually try to determine if the theoretical increase measure is more or less similar to what we measure.
Okay. And regarding the results, what can you tell us about the overall movement of the section?
Well, here in this first graph, you can see the total displacement of the track in the vertical axis, and in the horizontal, the different speeds of the train. And as you can see, there is an increase of the overall, of the total displacement of the rail, very close to what is said by the theory. The theory is marked by these curves in black. So we can see that the overall the global behavior of the section in terms of the total displacement of the track fulfills what is said by the theory.
Okay, it's great. It's great. Have the opportunity to check with real values what is happening in the real section with this theory. Mm-hmm. And if we focus especially on the ballast layer, what were the key observations?
Well, very similar. I mean, in general speaking, very similar to what is said, what I have said about the total displacement. The movements were around 25 millimeters when we are in the static cases, and there was an increase to 0.5 millimeters when we are modeling trains at 400 kilometers. Again, let's say we can say there is a normal behavior, very comparable with the result we obtain in the Spanish high-speed lines.
Okay, great. And now the most important questions. How did the Leica layer perform under dynamic test? Because this always is the real barrier between the designers and the decision to use our solution in railways.
Well, about the behavior of this Leica material inside the railway section, two main ideas. The first one is, as you can see here, the value of the movement is very, very little. It's less than 0.1 millimeter. That's the first thing. So very small movements. And the second is that the increase of the movement with the speed, which is what must be, because the theory says that, is again fulfills what is said by the theory. So again, very small movements and a good overall behavior.
So we can see the movement, the real movement, because we have very big scale. If the scale was smaller, probably we can't see any movement.
Any movement, yes, because actually the movement goes from 0.06 millimeters to 0.12 millimeters. So it's
Nothing.
it's nothing, let's say. But our equipment is able to measure so little movements.
Great. Now let's move to the fatigue test, Jose. How many axles have you applied in this fatigue test, and how much load in total?
Well, in the fatigue test, we have performed two types of tests, one with passenger train and other with freight trains. In the passenger trains, we have applied 1 million of axles, and each axle around 15 tons. So in total, 15 million of tons with passenger trains traveling at 300 kilometers per hour. In the freight part of the test, we use the same freight train with a speed of 80, 100, and 120 kilometers per hour, 300,000 axles, and in total around 5 million of tons.
And would you describe the permanent settlements curve obtained in the ballast layer?
Well, in the ballast layer is this graph in the top part of this. There is a steady increase of the settlement, the permanent settlement in the ballast layer. When we model this pass by of trains, it's quite a steady increase, normal, very similar to the one we have observed in other tests, and we can say that also the rate of the increase is quite, let's say, normal, quite similar to the one we obtained in the Spanish high-speed lines.
Because here in this graph, we can see when we finish the test with freight trains and when we start with
here
the passengers,
the fatigue test actually begins here,
okay.
And this increase or this part shows how the increase of the ballast permanent settlement when we have modeled the passenger trains, and from this vertical line the increase due to the freight train operation. The increase is quite similar, although in the freight train is a bit steeper, but it's very little. The increase is very little.
And probably we can say that it's normal.
Yeah, of course, because the load is more.
Okay, so great. And what about the LECA layer? What happened in settlement?
Well, here you can see, if we compare these two graphs, we can see that it's clear that the increase in the ballast, the rate of the increase in the ballast is much higher than the rate of the increase in the LECA. In LECA, actually, the permanent settlement is almost negligible after these 1 million of axles of passenger trains, and in the freight train there is a little increase. Mm-hmm. So we can say that the LECA layer has suffered very little fatigue during these tests.
Probably because the load that achieved to the first part of LECA layer is very, very small.
Yeah, I mean, due to the measurements that are obtained with the pressure cells that we have installed in the different interfaces, we have been able to measure the pressure. The pressure on the top of the LECA is around 20% of the total load applied by the trains of the actuators. So the value is not very. Let's say we can say it's small, and that's probably is the reason behind this little increase of the permanent displacement of the LECA layer during the fatigue test.
Jose, to conclude, what are the main takeaways from this work for railway designers?
Okay, as I have said before, during the last years, we have performed a lot of tests with, let's say, usual Spanish high-speed lines, and with all those results, we have been able to compare those results with the ones obtained in this section. When we have made that comparison, we can say, and as a global conclusion, that the behavior of this railway section, in which there is a layer of 1.1 meters of LECA, is perfectly valid, perfectly comparable to the, let's say, usual ones. And the second idea is that this LECA layer, which is, remember you that is below the subballast and the foam layer, it's able to handle perfectly the load imposed by the high-speed trains.
Okay, great. Jose, thank you very much. Now we are going to the main office of the Geotechnical Laboratory. We are going to answer your questions. Please feel free to ask what you need. Send us your comments, and in a few seconds, we are going to answer your questions.
Thank you.
Hello, everyone. Hello, Jose. How are you?
Hello.
Okay, we have different questions. We are going to starting with the first one. Alireza asks, how do you take into account the effect of soil underneath the embankment?
Sorry?
How do you take into account the effect of soil underneath the embankment?
Okay, well, this is something that has not been explained in the video, but the section that has been tested is composed by, from top to the bottom, from the rail and the sleepers that only are there to transmit the load from the actuators to the section. Then the ballast layer, subballast layer, the LECA layer, and then there is around 1.3 meters of embankment. Under that embankment, there is, let's say, the bottom of the metallic box. So there is no soil underneath the embankment, really, in the test. But we are confident in the results obtained because, as explained in the video, the pressures that arrive at the bottom of the box are very, very small. So there is no, say, influence on the results obtained from the, say, any type of soil that could be underneath the embankment.
Well, next one, I think that I can answer it. Jacob is questioning, is there a need for geotextile between the LECA layer and the overlying layers? Yes, we need a geotextile. We usually recommend polypropylene geotextile to keep the performance of the lightweight embankment, the performance in density, the performance in don't have fines inside the LECA layer. Next one, Joel is asking.
Actually, sorry, Raul. Yeah. I can add that to what Raul has said, that in the test in the FedEx track box, they install geotextiles both in the bottom of the LECA layer and the top.
Yeah, I have to say that this geotextile come from Solmax. So thank you very much to Solmax to help us to develop this part of the test. Okay, Joel, is there any diagrams with comparison between the same test without any LECA?
Yes, and actually, I think no, we haven't shown those diagrams in the video, but first of all, there was a webinar, a seminar in Lisbon last October. There I presented some of these diagrams, and I guess that LECA can provide you with a copy of that presentation. But more important is that we are now, after the finishing of the test, we are preparing a report, which is going to be public, because all these tests have been performed in the frame of a European project, and it's compulsory that we make all these the results public. So now we are preparing a public document that I hope that before summer it's ready in the FedEx web page for you to upload them. And in that document, in the last chapter, we finish all the presentation with a comparison between the result obtained here and results obtained in other sections for high-speed line without LECA.
Yeah, we are going to share the link after this webinar. We are going to share the link to download the document, and they can check the results. Okay, next one is Alideza ask again. We are not this LECA grains angular. Yes, you can find different type of LECA material or material produced in Avelar and produced in other parts of Europe. is round. So other providers of lightweight aggregates have this type of angular materials. Okay, Jorge,
sorry, Roland. And adding,
yep.
Of course, I guess that the question is that they are say quite rounded, and you are thinking in the shear resistance of this material. But I have to say that all the particles are very has a very high rugosity. So the shear resistance of the material as a whole, as an aggregate, is quite high. We are talking about friction angles of around 35 to 45. So high friction angles due to that rugosity, although they are quite rounded.
Yeah, Jorge, for the LECA layer under subgrade layer, was it necessary to confine the LECA layer knowing that no cohesion is between the particle is available?
Well, here in the test, the boundary of the section is the metallic box, so there is no problem in that confinement of the LECA layer. However, in real life, I mean, say in the real sections, some kind of confinement is necessary, and that confinement can be done by another geotextile or by little, say, layers of mineral material. It's something that must be designed to avoid to confine the material.
Yeah, we can use different types of ways to confine the material with standard aggregates and with walls. So we can share to Jorge in private meeting the different ways to work with these embankments. Okay, Veli-Matti is asking, what was the axle load with freight trains in fatigue test?
25 tons per axle. That value was under discussion with people from LECA, and we decided to make the test with a little higher value than the, let's say, normal axle load freight trains in Europe, which is 22.5. We decided to use 25 to be sure that the results can be used in the future in case in Europe this axle load of freight trains increases a bit.
Because the freight trains come from Eurocode. I think it was number 7. That's
I mean the load distribution. I mean the train was, I don't remember the number, but it will be in the document. It's a freight train that appears in Eurocode 1, the actions, and there we increased the load, because there in that train in Eurocode was 22.5 tons, but we decided to increase 25 for future applications.
Other questions, maybe this is one more general question. Have you tried to test LECA layer without horizontal constraints? Kind of odometer test.
Well, I mean, I don't really understand the point of your questions, but I can say several different answers. Perhaps one of them fulfills your requirements. In the test that you have seen in the video, we have not applied any horizontal load, and the horizontal constraint is said before the load, so the metallic box. In laboratory, let's say in the technical laboratory, we have performed a lot of tests with different type of confinements and constraints. We have performed some odometer tests, some triaxial tests, and direct shear tests also. But that's what I can say, that the constraint in our test is done by the metallic box, and in real life all these layers should have some confinement to have a good global performance.
This material works very well in odometric conditions, so we always recommend use the material in these conditions. Okay, Ray is asking, in which part of the embankment layer is the LECA layer replacing?
Well, as I said before, the section that was tested was composed by the ballast layer, the subballast layer, and foam layer. Both these two layers has let's say a depth of 60 centimeters, and just below the foam layer, we decided to install the LECA layer. So somehow the LECA layer is replacing the top part of the embankment.
Yeah.
And was decided to install or to construct the LECA layer in that part of the section, because in some occasions there was no embankment at all, and LECA layer can be installed just in the surface of the natural ground. So for both ideas, we decided to install the LECA layer just below the foam layer.
Yeah, Christopher is asking, how does the shear wave velocity profile look like?
Well, we didn't perform a real spectral analysis of surface waves to obtain a shear wave velocity profile as should be, because of the dimensions of the box didn't allow us to be confident on the results. However, we try to measure the shear wave velocity of the LECA layer, because this is very important to determine the critical velocity of the whole section. And the shear wave velocity of the LECA layer, with taking into account that, say, constraints we have during the measurements, was around 300 meters per second. So regarding the problem of the critical velocity, there was the critical velocity of the section, there was no problem at all, due to the presence of the LECA material.
Okay, we have a lot of questions. Juan Manuel is asking, in practice, how are the embankment shoulders constructed? Is it necessary to confine LECA type material with shoulders made of conventional fill? I think that we answer this question. This question
And
comes
I guess,
from Manuel Hurtado.
Raúl, and I guess that in that guideline that the Spanish branch of LECA is is finishing now. There are some diagrams of how to construct or to build these shoulders in the LECA for the LECA layer.
Yes, we are going to publish a new document where all the engineers can solve this question about how to use LECA in the infra project. If you have any doubts, you can contact us, and we can have a Teams and study your project. We have another questions. Let me. We have more questions about critical speed. Darius, have you done any shear wave velocity measurements in LECA material? Is versus in this material much different than normally? In this material, much different than normally assumed 250 meters per second in regular embankment material for assessments of critical speed value?
Yes, as I have said before, we perform some measurements of the shear wave velocity in the LECA material, and the result shows around 300 meter per second. So a bit larger, a bit higher than the value that Darius is saying.
Jose?
Yes. Do you have? I'm going to share. I know that I have some problems. Disable the camera now. Can you hear me better?
Yeah, maybe better. Yeah.
Yeah, I some problems with my connection. Well, as I was saying that we performed some tests to determine the shear wave velocity of the LECA material, and the value obtained was around 300 meter per second, so a bit higher than let's say this default value that Darius is saying in his question.
We go to the last one. We don't have more time, so we are going to answer by email the other questions. The last one is: could I get cross section of the test embankment? Was LECA made in Spain or Finland?
Well, of course, we can Raúl or the LECA from people from LECA can send you the section with any problem. And about the place of fabrication of the material used in the test was in Portugal, Alvear, I think.
Yes,
but Raúl can answer better that question, because the LECA provided us the material they wanted to use in the test.
Yeah, and can you, the section that was installed is a standard section for high-speed trains in Spain, right?
Yes, yeah. Except the replacement of that top part of the embankment with LECA material, but the other materials that compose the section are the same than we use in Spain for our high speed lines.
Mm-hmm. Okay, Jose. We have much more questions, but we don't have more time, so we are going to answer by email. Thank you very much for your cooperation. I would like to thanks to CEDEX. You did a great job, and I'm sure that the railway development is going to have a next step, yes, to the develop of this solution. If you want to share Any comments or any thoughts?
Well, actually, for us has been a pleasure to work with the people from LECA in this testing program in the frame of, as I said, European project called GeoLab. That's my first idea. And the second idea, reading the questions that are in the chat. As I said before summer, I'm completely sure that that we can distribute. I mean, you can download the document with all the results. But if you are not able to download, write to LECA, and because they are going to be able to provide you with the document. The document is going to be public on everything. All the measurements and all the work we have done can be public for you to use in your designs.
Okay. Thank you, Jose, again. Thank you for all the attendance. We keep in contact. Feel free to ask us by email, or for any of my colleagues from LECA Internacional. Thank you very much for your support.
Thank you.
Thank you.
Bye.